extending pluricanonical forms in algebraic geometry. So let's welcome him.
Okay, thank you very much for the introduction, and thank you for having me here. Just a disclaimer, this is my first colloquium talk, so if it gets too boring or too technical, just, let me know, and feel free to ask a question at any time. So I'm going to talk about some results concerning extending pluricanonical forms, especially in characteristic P and mixed characteristic. So before, let me start with some introduction and motivation. So I will be working over the complex numbers for now, but later we will move on to positive characteristic or mixed characteristic. So we studied algebraic varieties. So, and these are simply, you can think of them as sort of complex manifolds which are locally defined by, say, phi 1 equal to 0, phi L equal to 0, where these phi I are just complex polynomials. Okay, so some space that is locally modeled after the vanishing locus of a finite set of polynomials with complex coefficients. And our upshot, we want to understand the intrinsic geometry of X. So how do we do it? Well, the protagonist of this talk will be the canonical bundle. So this object will be denoted by omega x. And so by definition, this is just the top wedge power of the cotangent bundle of X. Okay, so this is a line bundle. And its local sections look like something as like a holomorphic function times dz1 wedge dzn. So these are just local holomorphic coordinates on your manifold, and this is what a local section of this line bundle looks like. Okay, so the punchline is that the global sections of omega x detect the geometry of X. Okay, so we will understand the geometry of the variety through the properties of the local section of this line bundle. So what do I mean by this? Let me make an example. So let's suppose that X is a Riemann surface. Or if you want a complex algebraic curve. And then, if you've played around with these objects already, you know that the most important invariant is the genus, which is just defined as the dimension of the space of global sections of omega x. So this is a finite dimensional vector space over the complex number, and its dimension is called the genus. And when X is a curve, the genus sees a lot of the geometry of X. So let me draw a table for you. So we distinguish three cases. When the genus is equal to 0, our X is just the complex projective line. So topologically, this is just a sphere. And omega x is anti-ample. So it's very negative, meaning the dual will induce an embedding in the projective space. When the genus is equal to 1, we have elliptic curves. So over the complex number, this is just C modulo lattice. And topologically, these are nothing but a donut. And in this case, omega x will be trivial. And instead, when the genus is at least 2, then we have what we call a curve of general type. And topologically, this is nothing but a donut with G holes. And these are characterized by omega x being ample. So in this case, omega x will give you an embedding inside the projective space. And these three sort of types of varieties, we will call them Fano, when omega x is anti-ample, Calabi-Yau, when it's trivial, and canonically polarized. When omega x is ample. Okay, so for curves, the picture is very nice. The genus detects sort of a lot of interesting geometry of the curve. What about in higher dimension? Well, the situation is a bit more complicated. Why? Because if you take global section of, let's say, the simplest possible algebraic surface, so the projective plane, you know, this thing has no, I mean, there is no global section of omega. And if you take X to be an Enriquez surface, so this is a K3 modular involution, then you also have that H naught of omega x is 0. So if you just look at the genus of these two surfaces, they are the same. They both have no non-trivial canonical form. However, they are very different. P2 is Fano, but the Enriquez surface is Calabi-Yau. So this is negatively curved and this is flat in some suitable sense. So what's the solution? The solution is instead of looking at just sections of omega x, we will look at sections of all the possible tensor powers of omega x. So let me introduce the definition. So I will call kappa of x the codarea dimension. And so this is an invariant that generalizes the genus and is defined as follows. It's defined by cases. So we set it equal to minus infinity if whenever I look at all positive tensor powers of my line bundle, this is 0. And if not, I set it equal to k, where k is the rate of growth of the space of global sections. So let me finish writing and this will be clearer in a moment. So if I look at the dimension of this space of global sections as a function of m, this thing will grow polynomially with a certain degree. That degree is the codarea dimension. So it will grow like m to the k plus some lower order terms. And this is what I call the codarea dimension. So it follows that the codarea dimension of x is either minus infinity or a non-negative integer which is at most the dimension of x. And now we are very happy because while the genus could not tell these two surfaces apart, the codarea dimension can. Codarea dimension of P2 is equal to minus infinity, but the codarea dimension of the Enriquez is equal to 0. So now, by looking at all the powers of the canonical, we can separate P2 from the Enriquez surface. And just to fit this classification in the old one here for curves, I can tell you what the codarea dimension is in this case. We have minus infinity here, 0, and 1. Okay. Now, this picture for it does generalize in dimension 2, but before telling you what it looks like, I need to introduce some more, one extra notion. So I'm going to say that x and y are birational if there exists a rational map inducing an isomorphism on a dense open. So for curves, this notion is sort of empty. Smooth curves are birational if and only if they are isomorphic. So this is not really interesting in dimension 1. In dimension 2 and higher, however, it is extremely interesting. The simplest example is the blow-up. So if you take A2, or I guess maybe C2, and you take a point, you can look at all the possible lines through this point. And the blow-up is an operation that replaces this point with a line, a projective line, which separates all the possible tangent directions. Oh, maybe I should put it like this. So we have this E, which is just a P1, and it's we call this an exceptional curve. So this map doesn't do anything away from this line, and it contracts this line down to a point. This is the simplest example of a birational morphism, or map. Okay, observation, the fundamental observation is that if you look at omega x times this curve E, so this guy here is just defined as the degree on E of omega x restricted to E. Here x is the blow-up. This thing is negative. So these these special curves are characterized by the property that omega x is negative when you restrict it on it. Okay, and so in some sense you would like to get rid of all these curves because I mean, you can keep blowing up C2 at different points and obtain many different birational models of the same variety. But, I mean, the simplest possible model that you have is just C2 without any curve blown up. So, this is the starting point of the minimal model program. Okay, so the conjecture called minimal model program is that if X is a smooth projective variety, then there exists a birational contraction to some other variety, which is omega x negative. This means that you're just getting rid of curves on which omega x is negative, such that one of two things happens. One, when the Kodaro dimension of x is negative, then y, there exists a fibration in Fano varieties. And when the Kodaro dimension of x is non-negative, then omega y is omega y times any curve is non-negative for every curve in y. So what this is a conjecture, but is known in many cases. What it's telling us is we take any projective variety, And then we run this contraction algorithm, which gets rid of these negative curves for us. And we arrive to a model where either your variety fibers into Fano varieties, so the ones that have negatively curved geometry, or you get to a variety where the intersection with any curve is non-negative. Okay? Any questions? Because so the idea is that I mean it comes from this term was introduced by the Italian School of Algebraic Geometry. So a minimal surface is one without -1 curves. -1 curves are exactly the ones that appear with a blow-up. And so what this process does in dimension 2 is exactly getting rid of all the -1 curves. Yeah. In dimension 2, literally what this is doing is you can recognize curves that come from a blow-up as the ones that have self-intersection -1. You take all of them and you keep contracting them. At each step, you are contracting a sphere, so by easy topological argument, since you are on a compact space, the Picard rank drops by 1 at every step, and after finitely many steps, you reach a minimal surface. Sorry? There is a fibration in Fano varieties, yes. Why? I mean, X is the variety that you start from, then you run some birational transformation that we understand fairly well, but let me not talk about it here. And then you get a new model on which this Fano fibration appears. Oh, no, the fibers. So what I mean is that if I take a point in here and I look at the fiber, this is Fano. So fibration in Fano varieties, this is what I mean. And there is another conjecture that sort of complements the picture, which says that, so this Y is called a minimal model. And the conjecture says that when Y is a minimal model, then omega Y is semi-ample. So what semi-ample means is that a multiple of this line bundle will induce a fibration on its own. But now, the fibers here are no longer Fano, but they are Calabi-Yau. So, very roughly speaking, if you put all these pictures together, these two conjectures tell you that whenever you have any variety, after running this MMP algorithm, you can always break it down into either Fano pieces or Calabi-Yau pieces, or if this fibration is birational, then you have that Y is canonically polarized. Sorry, Z is canonically polarized. So every variety can be constructed starting from 3 fundamental types of varieties: Fano, Calabi-Yau, and canonically polarized. Okay, so and I should mention, I mean, there is an intrinsic description of this Z, so, and we will need this later, but this Z is nothing but the proj of the canonical ring of Y. So what is the canonical ring of Y? This is just the graded ring given by global sections of the canonical divisor. So this is naturally a graded algebra, and it turns out that it's finitely generated. This is a big result of Birkar, Kashini, Hekon, and McKernan. And if you take the proj of it, you get what is called the canonical model of your variety. So maybe I should write it here. So in other words, when your variety has sections, by taking proj of this ring, which is an object that is completely intrinsically defined, you obtain you give your x or y, after a birational modification, you give it the structure of a Calabi-Yau fibration. So this decomposes in a sort of canonical way your variety. Okay. Now, hopefully I managed to convince you that sort of pluricanonical sections, that is, sections of this guy, are fairly important for understanding the geometry of our variety. Now, algebraic varieties, they naturally come in families. So if you have an algebraic variety that is given by some equation, if you perturb the coefficients of the equation a little bit, then your varieties will deform. And so it is a natural question to understand how do these sections behave under deformation. So this is the question. Oh, this is chapter 1, I guess, extension. So suppose that you have a one-parameter family of algebraic varieties. Then is the dimension of H naught xc omega xcm independent of the point? For all m greater or equal than 0. So I look at the global section on a fiber, and then I move the fiber, and then I'm asking, is the number of sections independent of the point? Or equivalently, you can look at, there is a natural restriction map from the total space to a fiber, and you're asking whether this thing is surjective. So this is why this is called an extension problem. This number being independent of the fiber means that on any pluricanonical form on a fiber can be promoted to a relative pluricanonical form on the total space. And so a big theorem of CU in 2000, I believe, says that over the complex number, the answer is yes. Now, this was still is a big deal. For several reasons. So a bunch of remarks. So the first one is that the proof is completely analytic. So although it's a theorem in algebraic geometry, the only known proof uses analysis. And it uses like very sophisticated analysis, some L2 extension theory of Osawa and Takegoshi. Yes, yeah. So there is no algebraic proof of this thing. But it was proven by Nakayama that if you assume MMP plus abundance, then you have CU's theorem. However, MMP and abundance right now are open, so this does not settle it. Why is this important? Well, so the main reason is the following. You know that, the main reason is that it's very useful for what is known as KSBA moduli theory. So what is this theory? Well, you fix an integer g, at least 2. Then we know that we have mg. This is the moduli space of smooth genus G curve. So this is a variety that parameterizes isomorphism classes of genus G curves. It's one of the most studied varieties in algebraic geometry. Now, this gadget is not smooth, right? And is not smooth for a very simple reason. Is not compact, I meant. And it's not compact for a very simple reason, is because if you take a smooth curve, you can always degenerate it to something that is singular. So sort of not every limit lives inside here. However, there is a natural compactification called the moduli space of stable curves of genus G, which is proper. And the adjective stable here is both a global and local condition. So stable curves here are curves that are at worst nodal and have omega c ample. So, like the picture suggests here, although you can degenerate a curve to something that is no longer smooth, you can make sure that whatever the limit is, it always falls into this class of very mildly singular curves. So you allow limits that are nodal, these are okay, but you don't allow limits that have sort of cuspidal singularities. These are non-nodal singularities. And it turns out that this is a compactification, and it's still modular, meaning deformations of a curve are parameterized by sort of arcs inside this moduli space. Now, KSBA moduli aims to generalize this picture to higher dimension. Okay, so replacing curves with higher dimensional varieties. But it is, I mean, now it's a completely worked out theory, but it took some good 40 years in order to understand what the right generalization is. So curves of genus G greater or equal than 2, this corresponds in higher dimension to varieties X such that the dimension of X is equal to the code-area dimension. So if you remember our table at the beginning, genus greater or equal than 2 corresponding to code-area dimension being exactly equal to the dimension, equal to 1. So these are the right generalization, except that is not really true. Why? Because again, the problem is that there are too many birational representative in the birational equivalence class of a given variety. So really what you should look here is canonical models, meaning varieties such that the dimension is equal to the code-area dimension, but you also ask that omega x is ample. And the good thing is that, so if you have a variety like so, you can always, so if x is as above, you can always make omega x ample by taking the canonical model. So if you have a variety with maximal code-area dimension, and you take x can, the canonical model, this was just proj of the canonical ring, then omega x can is ample. So even if you start with any variety with maximal Kodara dimension, you can always make a birational transformation that makes your canonical divisor ample. Okay, so you are selecting the good birational representative in its birational equivalence class that realizes this condition. Now, if you remember how this guy was defined, this is just the direct sum of all the spaces of global sections here. What Siu's theorem is telling us implies that is telling us that forming canonical model is compatible with restriction. So what do I mean? I mean that if I have a family of varieties X over C, then I can form my canonical model Xcan over the base, okay? And then I can look at a closed point inside my curve C and do the base change of this diagram. So I have XC here. Let me call this map F. And then I have Xcan, and I take the fiber over C. Cu is telling me that this fiber here is the canonical model of the fiber. So this is what I mean when I say that taking the canonical model is compatible with restriction to a fiber. The relative canonical model of a family is the family of canonical models of the fiber. This is because I have this restriction property for the space of global sections. So since Xcan of a fiber is given by proj of this thing, and every such section extends, this is what gives me the compatibility. And so this is the key input improving properness of KSBA moduli. Yes?
Do you have to impose some condition on the singularity of this
Yes. So there, you're right. I didn't want to get too technical, but yes. So sort of smooth curves of genus G generalize to canonical models, which are exactly proj of these things for smooth varieties of general type. Of course, again, you don't get a compact moduli space because you can still degenerate them to something singular. So stable curves generalize to something called stable varieties. Which, okay, so, I mean, there are a bunch of conditions, but the one that you want to remember is these are S2 schemes. They have log canonical normalization. Log canonical is some condition on singularities from the minimal model program. And they are at worst nodal. Yeah, exactly. Semi-log canonical is the non-normal version of log canonical. It's equivalent of asking, it was nodal in codimension 1. And again, you want omega to be ample. Yes. So this is some fairly technical condition. For the purpose of this talk, the key thing that you want to remember is this: S2. They need to be S2. Yeah, no, please. Oh, Alexiev. Yeah, I mean, I don't know. Sometimes people say that you need to put, okay, let me know. Okay, so now hopefully I managed to convince you that Siu's theorem is like quite important, not just for philosophical reasons, but really it has some very, very useful application when you start to play around with moduli theory in higher dimension. This is really a cornerstone of higher dimensional moduli theory. And also let me say, sort of this minimal model program, although it's still a conjecture in full generality, for varieties of general type is being completely established by a big paper of Birker, Kashinieckon, and McKernan in 2010. And the techniques in CU's theorem played a huge role in the proof of this result. So it's really, I mean, it's really it has very, very, very wide implications. Now, this was all over the complex numbers. And so now I would like to move into positive or mixed characteristic. So since our algebraic varieties are something that is locally defined by a bunch of polynomials, what I'm doing is just I'm changing the coefficient of our polynomials to a field of characteristic P, or, I don't know, a ring of mixed characteristic like Z or the p-adix. And all these constructions still make sense. So the question is now, does invariance of plurigenera still hold? So this is a very non-trivial question now, because if you remember, I told you CU's theorem is proven using analytic techniques. And that's all fun and games on the complex numbers, but if you move to like FP or FP bar, then those really don't make any sense. What is a metric on a variety over FP bar? I don't know. So it's really a non-trivial question here. And so the first remark is that so stated as it is, the answer is no. But for a sort of silly reason. So there were examples, so there exist families of surfaces. So X over, let's say spec of, I don't know, F2 or whatever, FP, T. So this is the positive characteristic equivalent of a small disk of radius 1, such that the general fiber, so the genus of the general fiber is strictly smaller than the genus of the special fiber. So, I mean, in other words, the genus jumps. But in all these examples, all the other plurigenera are deformation invariant. So if you take m greater or equal than 2, then you have invariance in this example. These examples come from okay, the first one I believe is Lang and Katsura and Ueno. This was in the 80s. And they consider respectively Enriquez surfaces in characteristic 2 and elliptic surfaces in any characteristic. And a bit later, I mean, actually much later, Su, which is not Cu, it's Su, he showed that the same is true even for canonically polarized surfaces. But again, it's really a phenomenon concerning the genus, not the higher plurigenera. And this is not too surprising, actually, if you think about it. Why? Because this number is a Hodge number, okay, if you think in characteristic 0. And it's very easy to see that Hodge numbers are constant in families in characteristic 0. Why? Because if you have a smooth families, all fibers are diffeomorphic, and then the Hodge decomposition plus upper semi-continuity will easily tell you that every Hodge number has to be constant. But it's well known that Hodge theory completely breaks down in characteristic P, so it's not too surprising that the genus here fails to be deformation invariant. So the next question, since, I mean, for moduli purposes, having invariance for all m large enough, or even for all m divisible enough, that's perfectly fine. Then the next question is, do we have invariance for all m greater or equal than 0 divisible enough? So when I say divisible enough, what I mean is all multiples of a sufficiently large number. Okay, so all the multiples of 10 millions, maybe, I don't know. For moduli purposes, like if we had a positive answer to this question, that's literally as good as having the formation invariance of all of them. Why? Because what we care about is forming proj of this canonical ring in family, and up to replacing the ring by a Veronese, I mean, we get the same thing geometrically. The punchline is that, and this was observed by myself and Collari independently, the answer to this question is also no. And now this has much more serious implications. Sorry? Hodge theory to, I mean, it would be nice if you had it, but you don't have Hodge theory in characteristic P. Like, Hodge decomposition is just false. In this, yeah. I'm gonna write a more precise statement now. But yes, I mean, also in the general type case, it can fail. I'm going to give an example in Codare dimension 1 because the construction in the general type case is a bit involved. But hopefully I can give you a taste of sort of what is that goes wrong. So the theorem, more precisely, is the following. So there exists phi. Now I'll have to work with pairs. So if you don't know what a pair is, it's just a variety plus some formal sum of codimension 1 subvarieties called a divisor. And I mean, essentially, most of the statements of the MMP work with, instead of playing with omega x, we just twist it by this divisor. Roughly speaking, this amounts to considering pluricanonical forms with poles prescribed along this divisor. You can get rid of B, it's just that it's a bit complicated, and I mean, to get an idea of what's going on, I want to, it's easier if I just allow myself to incorporate a divisor. So anyways, so C here is just some, let's say, spec of R, where R is a mixed characteristic dvr. So think of like p-adics, for example. So that there exist smooth families of terminal surface pairs of Codare dimension 1 such that for all m greater or equal than 1 divisible enough, the dimension of pluricanonical forms on the generic fiber is strictly greater than the dimension on the special fiber. Sorry, the opposite. Now, okay, I need to speed up a bit. Let me give you the construction, sort of how do we get this thing. So what we are going to leverage is the fact that in characteristic 0, if you take an abelian, a group scheme over a base, then it's always smooth. This is no longer true in positive and mixed characteristic. So So we take E. So this is over our base DVRC. This is a family of elliptic curves. And we take M, a non-trivial p-torsion line bundle, such that when I restrict to the central fiber, it becomes trivial. So this you can always do, because line bundles on elliptic curves corresponds to points on the elliptic curves, essentially. Elliptic curves in p-torsion points on an elliptic curve over the complex numbers, they form a group that is isomorphic to Z mod p squared. In characteristic P, an elliptic curve has always at most p torsion points, either p or 0. So this means that there is some line bundle on the generic fiber here that is p torsion and non-trivial that specializes to something trivial on the central fiber. Okay. Then I'm just going to take P1 over our parameter C with coordinates ST. And then let me consider the following sections. So I take mu. This is a global section of M to the P. And then I'll take S to the P minus 1 times T. And this is a global section P1C OP. Okay. Then let me call Z the fiber product of E with P1. So this is a family of elliptic surfaces, a very boring one, admittedly. But then I take this line bundle, which is just M box product with O1. And I take a section, sigma, which is mu box product with SP minus 1 times T. Okay, so this is a section in L to the P on Z. Oh, this is just short for saying, I mean, it's a product. I pull back from one factor, I pull back from the other, and I take the tensor. Yeah. Yeah, yeah. It's just, I mean, I should write like projection 1 pull back, tensor projection 2 pull back. Yeah, yeah, that's what I mean. Okay. And then, okay, and then I consider X to be, I take Z, and then I extract the pth root of this guy. So it's a standard branch cyclic covering construction. And then, okay, I need to normalize just to get rid of some singularities. So this guy just maps to Z, which maps to P1 over C via the second projection. Okay, and then, okay, I need to tell you what B is, but it's not really important. So B will be some small number, and pull this map here, I call it F, and pull back off a sum of many points. But, so, what's going on here? So let me explain with a picture. Yeah. Okay, so what did we do? We had this very boring family, which is Z. Z is just a product family, right? So this is P1 on the generic fiber, P1 on the special fiber. This is Z special fiber, Z generic fiber, and this is just a very boring family of elliptic surfaces. Okay, then we took this cover. How does this cover work? Well, so it will be, I mean, okay, it's again a smooth family of surfaces. This is just a computation. But what matters is what happens to the elliptic fibration. So if you look on the generic point, what are we doing? We are extracting the pth root of this section mu twisted by this sp minus 1 times t. So what this means is we gain 2 multiple fibers over 0 and infinity, but okay. And then we are replacing the general fibers here with an étale P21 cover of the corresponding elliptic curve. So something like this. And that's fine. This is a nice elliptic surface. But what happens when we specialize? So when we specialize, you see, this mu becomes a pith power. Or if you wish, it becomes just a constant, because we took m to specialize to the trivial line bundle on the central fiber. So really, there is no contribution from the m factor when you are doing this cyclic cover. All that you are doing is you are extracting a pith root of the variable t. And what this translates to, geometrically, is that you don't have this nice elliptic fibration. You are just replacing every fiber with a thickening of the original fiber. In other words, this map here factors through what is called the Frobenius map on P1. So Frobenius is it's a map that just exists in characteristic P. Topologically, it's an isomorphism, so it's just the identity at the level of topological space, but on the level of function is given by raising every function to the pth power. And so in other words, what goes wrong is that on the generic fiber, you have a contraction, but here you don't. You have this factorization through a finite morphism, and this is exactly what causes the plurigenera to jump. This is something that cannot happen in characteristic 0 because you cannot find a line bundle that is torsion generically but then trivial on a special point. Any questions? Okay, so in the last 5 minutes, maybe let me tell you. Yes.
So the result is negative, right?
Yes.
So I don't quite remember. So the negative result implies what? Implies how do you connect to the previous question?
Oh, yeah. Right, sorry, maybe I should have said this. But the point is, so having deformation invariance of all sufficiently divisible plurigenera is equivalent to the canonical model, forming the canonical model being compatible with base change. Now, whatever the canonical model is, the canonical model is always a contraction. So a contraction is a map f from x to y such that the push forward of OX is equal to OY. Okay. Now, what goes wrong here is that the map from this map f from x to P1 over C, this is a contraction. It can be checked that this condition is satisfied. It's just a computation. However, when you restrict to the central fiber, this condition fails. The reason it fails is that there is something called Stein factorization. And this says that if you have f from x to y, any morphism, like completely proper, but okay, then you can always break it down like so. So there exists a factorization like so, where this is a contraction, and this is finite. So forming the Stein factorization always commutes with flat base change. So that's why, since this whole thing is a contraction, it remains a contraction on the generic fiber. However, really, just by checking by hands, you see that when you restrict on the special fiber, this morphism factor through the Frobenius, and this is finite. So you see that the Stein factorization of the central fiber has a non-trivial finite part. So in particular, it cannot be a canonical model because a canonical model is always a contraction. This is what it boils down to. And the trick is that sort of in characteristic 0, this condition is usually thought as a morphism with connected fibers. This is completely false in characteristic P. Frobenius has connected fibers. It's a homeomorphism. But it's not a contraction. The push forward of the structure sheaf via the Frobenius is a vector bundle of rank like P to the dimension. So there is this weird finite map which is a homeomorphism but is not an isomorphism at the level of functions. And that is what that's what goes wrong. Sort of topology and algebra mix in a very unpleasant way. Okay, maybe. I mean, yes and no. I mean, this is a characteristic P phenomenon. The field doesn't need to be finite, but yes. I'm almost out of time. Let me just mention two things before I finish. This thing has very strong consequences. If you remember at the beginning, I mean, halfway, I said that Siu's theorem was fundamental in proving that KSBA moduli spaces are compact. Okay, this is false in characteristic P. So the theory breaks down. So that's a bit worrisome because you would like to have a moduli theory that works even in characteristic P or in mixed characteristic, especially if you're interested in applications to arithmetic geometry. The other thing that I wanted to say, and let me conclude with some at least positive result, is that at the beginning I said Nakayama showed that if you have MMP in abundance, then you can recover Siu's theorem. So the question is what happens in characteristic P in mixed characteristic if you assume MMP in abundance? Well, you can't recover Siu's theorem because this violates Siu's theorem, and you have MMP in abundance in this example. However, what is true is that if you have a smooth family and assume MMP and abundance, then the following is true. There exists some positive integer e such that for every m greater or equal than 0 divisible enough, when I look at the space of m pluricanonical sections on the central fiber, and then I take the p to the eth power, so I take m pluricanonical sections, then I raise them to the p power, the p-eth power. This guy is inside the image of the restriction map. So in words, the statement is for every m divisible enough, you take a pluricanonical section, you would like to be able to extend it, you can't, but there is a fixed p-th power that works for every m divisible enough, such that whenever you take this section and you raise it to the p-th power, then it extends. And the punchline here is that this p-th power works for every m. So you have this sort of extension up to p power for all m divisible enough. And this is literally the best that you can hope for by this example. For smooth varieties, actually, it's okay, like for all m. The trick is, first you prove it for m divisible enough, and then there are these cyclic covering tricks that are, plus some multiplier radial techniques that allow you to get it for all m. Yes, so like this kind of phenomenon, like it fails even for, I have an example, I put it on archive a few months ago. There are families of 7 folds in characteristic 2 where you have jump of plurigenera. Yes, for all m divisible enough, even asymptotically. So it's really hopeless. I mean, you have to deal with this thing. Yes. Okay, sorry for going over time. Yes. It can also go wrong. That's a good point. No. The idea is the same. So really, what I used here is that I mean, the point is that I can have a DVR and a family of elliptic curves, right? Such that when I look to sort of E eta p to E c p, this thing is not injective. So there is this specialization map and it's not injective. This is sort of the key input that goes. So in mixed characteristic, this is automatic essentially, because you always have z mod p square points here and z mod p or 0 here. But if you want to work in equal characteristic, you can just take a ordinary elliptic curve, so something that has p torsion points, and degenerate it to a super singular. And then again, you will see this phenomenon happening. Yes. For the general type case, you play the same game, but instead of using an elliptic curve, there is this Del Pezzo surface that was constructed by Maddock, and it's a Del Pezzo surface that has this property. So this is very weird. It has like one-dimensional irregularity. In characteristic 0, this thing doesn't exist because of Kodaira vanishing. But it exists, and it turns out that its Picard scheme, it's a GA. So you have again a 2 torsion line. It's in characteristic 2, and you have a 2 torsion line bundle that specializes to something trivial. You play the same game and you get something even worse. Correct. No. This is no. Like the vibration is like is not even flat typically. The reason is the following: if you take, take a surface, imagine taking a surface of general type, so maximal Kodaira dimension, with like I don't know, semi-ample canonical. Then what this canonical model does is it will contract all the curves that have 0 intersection with it. So it will be something birational. In particular, is not flat. In the sort of in this extension problem, you mean? But in the characteristic 0, there is no problem. Like the theorem works. Yeah. I mean, no, it's not that you have a smooth vibration, but so what goes wrong here is that so you have X to the canonical model over some base, f. And so f is a contraction, i.e. the push forward of OX is equal to OX can. And in characteristic 0, what happens is that this thing remains true fiber-wise. So FC is a contraction for all C in C, i.e., again, FC push forward of OXC is equal to OXC can. So abstractly, you could say when this morphism is this vibration induced by the canonical divisor, then forming time factorization commutes with any base change, not just flat ones. This is sort of what is special about characteristic 0. And this is what fails in characteristic P because of this weird, purely inseparable phenomena. I mean, you can think of it as, I mean, as I said before, sort of in characteristic 0, requiring this condition, the contraction condition, is very close to asking for a map to have connected fibers. Now, intuitively, sort of having connected fiber is stable under base change, right? I mean, if I do the base change here, and I look at FC, well, if F had connected fibers, FC will also have connected fibers. So you expect this thing to keep holding. The problem is that this is completely false in characteristic P. There's plenty of map with connected fibers that are not contractions.
Further questions, comments? Okay, if this is not the case, then nothing is speaking.
Thank you.